Welcome back to Teaching Statistical Thinking. In our last video, we talked about transforming variables with specific focus on standardization. Remember, standardization takes a variable, subtracts the mean, and divides the standard deviation so that the new variable has a mean of 0 and a standard deviation of 1. Standardization is going to play a big role in this video, so don't forget. Today we're going to talk about a specific shape of a distribution that's called a bell shape or a normal distribution. And we'll also be talking about how the empirical rule applies to a normal distribution. Many of the variables in daily life follow what's called a bell-shaped distribution. The bell shape is centered around the mean, and you'll see that it can take various spreads. This normal distribution has a very tight spread. This normal distribution has a very wide spread. The means and spreads of the normal can vary from distribution to distribution, but what stays the same across all of them is the functional form that creates this distribution. I'm going to write this down so that you see where it comes from, but don't feel nervous because it's a little bit complex. The functional form is 1 over the square root of 2 pi sigma squared is the first part. Pi is just a constant. It's 3.14 ... Sigma is the Greek symbol sigma, stands for the standard deviation. It's what controls the spread of that normal curve. The second piece is E, which is another constant, 2.17 ... So it's just a constant, but we represent it by E, raised to the power minus our variable x minus mu, the quantity squared, over 2 sigma. Mu, another Greek symbol, is what controls the mean, or the center of the distribution. So each of these curves follows the same form. Pi and E are just constants. Mu controls where the center of the distribution is, and sigma controls the spread. Now, one of the very nice things about the normal distribution, and that I want you to remember, is something called the empirical rule. It's also sometimes called the 68, 95, 99.7 rule. And here's how it works. If you have a normal distribution, regardless of its center and its spread, if you mark off one standard deviation, minus 1 SD plus 1 standard deviation, about 68% of the data observations fall in that interval. If we mark off 2 standard deviations, plus 2 and minus 2, about 95% of your observations fall within that range. And finally, if we mark off 3 standard deviations and minus 3 standard deviations, approximately 99.7% of our observations fall in that range. That's going to come in very useful. Recall when we standardized a variable, we started off with the original variable, okay, and suppose that it has a normal distribution centered at the mean and a particular standard deviation. If we standardize that variable, and I'm going to call that standardization z, we took our original variable, subtracted the mean, and divided by the standard deviation. That new variable has a distribution that's normal with a mean of 0 and a standard deviation of 1. That means we're going to be able to use this empirical rule to estimate percentages for a normal that has any particular mean and standard deviation. And I'll show you how that works in a minute. You now know the 68, 95, 99 marks off 1, 2, and 3 standard deviations, but there's normal tables, or your calculator or computer will calculate the percentage for other standard deviations. Here I've listed about 10 of them that we'll use in a problem that's coming up. In 2003, of babies born in North Carolina, the mean of their birth weight was approximately normally distributed with a mean of 7.2 and a standard deviation of 1.4. So I've drawn a normal curve here centered at 7.2 with 68% of the area between plus and minus 1 standard deviation, about 95% within plus and minus 2, and about 99.7 within plus or minus 3. Suppose I wanted to estimate what percent of the babies born in North Carolina had birth weights greater than 9.5. 9.5 falls about here. It's further away than 1 standard deviation, but not quite 2. I'm going to mark 9.5 on my curve here. And I want to approximate the area to the right, because that represents the proportion of babies with birth weights greater than 9.5 pounds. To calculate that area, I'm going to use my standardization transformation. Remember, 9.5 minus the mean of 7.2 divided by our standard deviation gives us 1.5. 9.5 is 1.5 standard deviations above its mean. If I use my standard normal table, it gives me for a z-score, which is my standardized score of 1.5, it says 86.6% of the area is between plus and minus z. So I know that 86.6% of my area is within 1.5 standard deviations. I also know the area under the curve has to be 100%. So 100 minus 86.6 leaves 13.4% of the area in the tails. I only want one of the tails, so I need to do 13.4 divided by 2, and I know that 6.7, or about 7% of the babies, weighed more than 9.5 pounds. Easy? Let's do another one. What percent of babies were less than 7.9 pounds? Okay. 7.9 falls about here. Okay. So we know it's within 1 standard deviation of the mean. Standardizing, 7.9 minus 7.2 over 1.4, we know we're at 0.5 standard deviations above the mean. We want the area to the left. Okay. So what percent of the babies weighed less than 7.9? Again, I'm going to refer to my standard normal table. 38.3% of the area is within plus or minus 0.5. That means 100 minus 38.3, 61.7 falls in the tails. I want half of that, so that's about 30.9. Okay, so I want the middle 38%, 38.3% plus 30.9. That means 69.2% of the area is below 7.9. About 69% of my babies, or North Carolina babies, had weights less than 7.9 pounds. Okay, take it one step further. Now I want to estimate what percent of the babies had between 7.9 and 9.5 birth weights. Okay. We know that the 7.9, we saw 38.3% within 0.5 standard deviations. We know that (86.6) had within plus or minus 1.5 standard deviations. We want just this area, the difference between 7.9 and 9.5. Okay. So we know that that's going to be 86.6 minus 38.3, which is 48.3, and now we need to divide it by 2. And it's about 24.1%. We'd estimate that about 24.1% of our babies had birth weights between 7.9 and 9.5. Now these are just 3 simple examples. If you have a full normal table or a calculator or computer, you can calculate these percentiles for any normal distribution simply using standardization and a standard normal table. That's the end of the video of today on normal distributions, and this is everything you're going to need to know going forward in using normal distributions. This ends the part of the course where we talk about distributions for a single variable, and next time we're going to start talking about relationships between 2 variables, and that's where the statistics really gets fun. So see you then. Now let's see whether our students got it. I'm going to give an example that requires you to understand standardization and using the empirical rule. So come on in, Jake. Okay. I'm going to use the example of our North Carolina babies. Remember, their birth weights followed a normal distribution centered at 7.2 with a standard deviation of 1.4. I want you to find for me what percent of the babies had birth weights between 4.4 and 5.8.
Okay, so the distance between 4.4 and 10, these are both 2 standard deviations away from the mean of 7.2. So the distance and the area that those have between them is about 95%. And 5.8 is 1 standard deviation away from the mean of 7.2. And the distance between 5.8 and 8.6 is about 68%. So to find the area between these 2, we would do 95% minus 68% divided by 2, because we only want this half, not the other half. So let's get my nifty subtraction. (27% over 2 would be 13.5%. Is that right?
You got it. Good job.